Hello everyone. In this video, we shall discuss the double angle identities and some examples that will show applications of this double angle identities. So when we say double angle, we mean by, let's say, sine of 2 times a. So that means that the parameter of the trigonometric function may be expressed as 2 times some angle a. Now, to derive the double angle identities for sine, cosine, and tangent, we will be needing the sum and difference identities. So whenever we have sine of A plus B, this is expanded as sine of angle A times cosine of angle B plus cosine of angle A times sine of angle B. Now, for the sum identity of cosine, then we have cosine of A times cosine of angle B minus sine of angle A times sine of angle B. Now, for tangent of A plus B, then this is expanded as tangent of angle A plus tangent of angle B over 1 minus tangent A times tangent of B. So we shall use this sum identities for sine, cosine, and tangent to derive the formulas for sine 2a, cosine 2a, and tangent of 2a. So let's derive first the formula for sine 2a. So sine 2a can be expressed as sine of a plus a. So using the sum identity for sine, then we have sine of angle A times cosine of angle A plus cosine of angle A times sine of angle A. Now, if we use commutative property for this product, then cosine A times sine A is the same as sine A times cosine of A. So simplifying this sum, then we get 2 times sine of angle A times cosine of angle A. And that's our formula for sine of 2a. Now for cosine 2a can be expressed as cosine of a plus a. So using the sum identity for cosine, we get cosine of angle A times cosine of angle A minus sine of angle A times sine of angle A. Cosine of A times cosine of A is cosine square A. And then sine of A times sine of A is sine square A. So therefore, cosine of 2a is expressed as cosine square A minus sine square A. Now observe that these are squares, so we can use the Pythagorean identity to derive other formulas for cosine of 2a. So if we are going to use cosine square A is equal to 1 minus sine square A from the Pythagorean identity, then we get the following expression. And then simplifying further, we get 1 minus 2 times sine square A. So that's our formula for another formula for cosine of 2a. Now, this time, if we are going to replace sine square A by 1 minus cosine square A, then we get this expression. And simplifying further, we get 2 times cosine square A minus 1. So this thing is another formula for cosine of 2a. Now for tangent of 2a, so using the sum identity for tangent of 2a can be expressed as tangent of a plus a. So we have tangent of the angle A plus the tangent of the second angle A over 1 minus tangent A times tangent of A. Now, in the numerator, tangent A plus tangent A can be simplified as 2 times tangent of A, while in the denominator, tangent of A times tangent of A is tangent square A. So this is our formula for tangent of 2A. Now, in order to illustrate these formulas, now let's consider, let's say, sine of let's consider the angle 5 pi over 6. And 5 pi over 6, a sine of, no, not 5 pi over 6. Let's think of another angle. Let's say pi over, 2 pi over 3. Oh, or 4 pi over 3. Let's consider 4 pi over 3. Let's erase this. Let's consider sine of 4 pi over 3. Now, if you recall that the value of sine of 4 pi over 3 is negative square root of 3 over 2. Now, this is because the reference angle of 4 pi over 3 is pi over 3, and the terminal point of pi over 3 is 1 half comma square root of 3 over 2. But since 4 pi over 3 is in the third quadrant, this terminal point will be negative 1 half comma negative square root of 3 over 2. So since the sine function is defined as the y-coordinate of the terminal point, wherein the terminal point lies on the unit circle x squared plus y squared equals 1, then sine will be negative square root of 3 over 2. Now, this 4 pi over 3 can be written as sine of 2 times 2 pi over 3. So that means in the double angle formula of sine 2a, we can use 2 pi over 3 as our angle A. So that means this sine of 2 times 2 pi over 3 is equivalent to 2 times sine of 2 pi over 3 times cosine of 2 pi over 3. So if we get the values of this, sine of 2 pi over 3 is positive square root of 3 over 2, while cosine of 2 pi over 3 is negative 1. So simplifying this, we get 2 times square root of 3 over 2 will be square root of 3, and the square root of 3 multiplied by negative 1 half is negative square root of 3 over 2. So this verifies, this illustrates the double angle formula for sine. So you can also verify on your own using the same angle for pi over 3, for cosine of 2a and for tangent of 2a. Okay, now, so let's have the following problem. So this time, let's fill in the blanks. We're given with 2 times sine of 18 degrees times cosine of 18 degrees, and it is said to be equal to sine of blank. So based on the form of this equation, we can treat this as 2 times sine of the angle A times the cosine of the angle A. And this must be equal to sine of the double angle, or 2 times A. So that means if A is 18 degrees, then that means 2 times A will be 2 times 18 degrees, which is 36 degrees. So the missing information here must be 36 degrees. Now for the second one, we have blank equals cosine square 6x minus sine square 6x. So if you are going to apply the double angle formulas, cosine square of an angle minus sine square of the same angle is the double angle for cosine. So this is our A, cosine square A minus sine square A. So A is equal to 6x. And cosine square minus sine square of the same angle is double angle for cosine. So the blank here must be cosine of something. And that something must be 2 times A. So it's going to be 2 times 6x, which is 12x. So cosine 12x is the missing information for this particular example. Now for the last bullet here, we have tangent of blank is equal to 2 times tangent of pi over 7 over 1 minus tangent square of pi over 7. So in here, we see that this is the formula for the double angle identity for tangent. So pi over 7 is 3. So which means that we need 2 times A, which is 2 times pi over 7, which is 2 pi over 7. So the missing information here must be 2 pi over 7. Okay, for our next examples, we are going to prove identities that involve double angle formulas. So in here, let's prove that 2 sine square a plus cosine of 2a is equal to 1. So let's start with the left-hand side. The left-hand side is written as 2 sine square a plus cosine of 2a. So from this particular expression, we have a double angle for cosine, so which means that we're going to use an identity for this one. And we know that cosine 2a can be replaced by cosine square of a minus sine square of a. Now you can also use the other formulas, but you can do it on your own or by yourself. So in here, 2 sine square a plus cosine square a minus sine square a is now simplified as sine square a. That's because we have 2 sine square a minus sine square a is positive sine square a. And then we have plus cosine square a. But from our Pythagorean identity, we know that sine square a plus cosine square a is equal to 1, which is our right-hand side. So this proves this particular identity. Now for the other one, we have 2 times tangent of u over 1 plus tangent square of the angle u equals sine of 2 times u. So in here, we can start with the left-hand side, which is 2 times tangent of u over 1 plus tangent square of u. So based on the previous videos that you've encountered in proving identities, one technique in proving is we can change the other trig functions in terms of sine and cosine. So by the ratio identity, we know that tangent is sine over cosine. So this means that tangent of u may be replaced by sine of u over cosine of u. So same thing for the denominator. That's going to be sine of u over cosine of u quantity square. So this can be simplified into uh, 2 times sine of u over cosine of u. Okay, all over, this one will be 1 plus sine square of u over cosine square of u. So combining in the denominator, the LCD will be cosine square of u. So cosine square of u times 1 is cosine square of u. And then cosine square of u times this fraction will be sine square of u. And then we just copy the numerator, which is 2 times sine of u over cosine of u. However, cosine square of u plus sine square of u using the Pythagorean identity will be simplified into the value of 1. So this means that this thing is equal to 2 times sine of u over cosine of u all over 1 over cosine square of u. Now this complex fraction when simplified, so we copy the numerator and then we multiply that by the reciprocal of the denominator, which is cosine square of u. And then cosine of u will cancel out. Cosine square of u will become cosine of u. So this becomes 2 times sine of u times cosine of u. But this is familiar because this is can be simplified into the double angle formula for sine. So this is equal to sine of 2 times the angle, which is our right-hand side. And this proves this particular identity. Okay, next, let's have 1/2 of tangent of 2 times y equals 1 over cotangent of y minus tangent of y. So first, we can manipulate the left-hand side and then replace We can replace this by tangent of 2y is replaced by tangent of or 2 tangent of y over 1 minus tangent square of y. Now in here, 1 half times 2, so 2 will cancel out. So this will just be tangent of y over 1 minus tangent square of y. So we can replace this in terms of sine and cosine. So we can write that as sine of y over cosine of y all over 1 minus sine square of y over cosine square of y. So combining in the denominator, we get cosine square of y as the LCD. And then in the numerator of this fraction, we have cosine square y minus sine square y. And then the numerator will still be the same. It is sine y over cosine of y. And then simplifying this further, we get sine of y over cosine of y multiplied to the reciprocal, which is cosine square y over uh, cosine square y minus sine square of y. So we can cancel out the cosine of y here, and cosine square y will become cosine of y. So this is equal to sine of y times cosine of y over cosine square y minus sine square of y. So this is the simplified version of our left-hand side in terms of sine and cosine. Now, in order to prove the identity, we have to manipulate the right-hand side, and also we have to write it in terms of sine and cosine. So the 1 over cotangent y minus tangent y can be written as 1 over cosine y over sine y minus sine y over cosine y. So if we are going to combine in the denominator, the LCD will be sine y times cosine of y. And then sine y times cosine of y multiplied to this fraction. We will get cosine of y times cosine of y, which is cosine square y, minus sine y times cosine y multiplied with this fraction will be sine y times sine y, which is sine square y. And then we just get the reciprocal of this. So we have sine y times cosine of y over cosine square y minus sine square y. So the left-hand side here and our right-hand side are equivalent. So this proves our identity. Okay, and then finally, we apply these double angle identities to find the specific values for our trigonometric functions. So the problem here states that we consider that tangent of the angle alpha is equal to negative of 1/2, and cosecant alpha is greater than 0 or positive. And we are tasked to determine the values of sine to alpha, cosine to alpha, tangent to alpha, cotangent to alpha, secant of 2 alpha, and cosecant of 2 alpha. So if we are going to use the double angle identities, so this sine of 2 alpha is equal to 2 sine of alpha times cosine of alpha. And then cosine of 2 alpha can be written as 2 cosine square of alpha minus 1. And then tangent of 2 alpha is equal to 2 times tangent of alpha over 1 minus tangent square of alpha. So in order to solve the values of this sine, cosine, and tangent of 2 alpha, we need to get first the values of sine alpha, cosine alpha, and tangent alpha. However, we already have tangent alpha, so we can already solve this tangent of 2 alpha. But how do we get the values of sine alpha and cosine alpha given the following conditions? So let's solve it in another um, slide. So tangent alpha is equal to negative 1 half. Given that the cosecant of alpha is greater than 0. Okay, so in this case, we have to locate first the terminal point of alpha. So tangent of alpha is negative. That means the terminal point of alpha is in quadrants 2 or 4, while whenever we have cosecant alpha is positive, that means the terminal point of alpha is in the quadrant 1 or quadrant 2. So getting the common quadrant, so we see that the terminal point of alpha is an element of quadrant 2. And in quadrant 2, the x and y coordinates would be negative for x coordinate and positive for the y coordinate. So if we are going back into the definition of the tangent function using the circle x squared plus y squared equals r squared, then tangent of alpha is defined as y over x. So in this case, since the y coordinate is positive, then we have y equals positive 1. And since the x coordinate is negative, the negative sign will be absorbed by 2. So that means x is equal to negative 2 and y is equal to positive 1. So using this particular relationship, we can solve for the value of r. So in that case, we have 4 plus y squared is 1 equals r squared. So that's going to be 5 equals r squared. And r is plus minus square root of 5. However, we have to take positive value because r is the radius of this circle and the radius is positive. So since we already have the value of r, now we can get the value of sine alpha and the value of cosine alpha. Sine alpha is y coordinate over r. I'm sorry, the value of y over r, and cosine alpha is the value of x over r. So which means that we have y is, what's the value of y? Y is 1 over r is square root of 5, and x is equal to negative 2, and r is square root of 5. So since these are not our final answers, now we will just substitute them first into the respective formulas in the previous slide. So now sine 2 alpha can now be solved as 2 times 1 over square root of 5 times negative 2 over square root of 5. So this gives us 2 times 1 times negative 2 is negative 4 over square root of 5 times square root of 5 is positive 5. So the value of sine 2 alpha is negative 4 over 5. And in this case, we can solve for the value of cosecant 2 alpha by just getting the reciprocal of sine, which is negative 5 over 4. Now for cosine 2 alpha, we get 2 times cosine alpha is negative 2 over square root of 5, quantity square minus 1. And this is simplified as 2 times positive 4 over 5 minus 1, which is 2 times 4 over 5 is 8 over 5, minus 1 is positive 3 over 5. So the value of cosine 2 alpha is positive 3 over 5, and that means secant of 2 alpha is equal to the reciprocal of this, which is positive 5 over 3. And then tangent of 2 alpha, that's going to be 2 times tangent of alpha is said to be negative 1 half over 1 minus negative 1 half squared. So this is going to be negative 1 for the numerator. For the denominator will be 1 minus positive 1 fourth. That's going to be negative 1 over 1 minus 1 fourth is 3 fourths. And this is going to be negative 4 over 3. And then cotangent to alpha is just the reciprocal of negative 4 over 3, which is negative 3 over 4. So these are the values of the 6 trigonometric functions using the parameter 2 times alpha. So this ends our video for double angle identity. So I hope that you learned something from this video, and do not forget to subscribe to my channel. Thank you for listening.